for example number 3, we're asked to sketch the graph of f of x, where f of x is equal to x minus 1 over x. And we're asked to do this using a 6-step procedure that was given at the beginning of the section. So I'll do this in exactly those steps. So step number 1 is to first locate any symmetries. To do that, we'll check f at x, f at negative x, and negative f of x. So of course f of x is just x minus 1 over x. F of negative x is negative x plus 1 over x. And negative f of x is negative x plus 1 over x. So the two that match are here, and this leads us to this being an odd function. So we know that there's symmetry along the origin. Okay, let's go ahead and take a look at part 2. So now we need to locate any points where f is not defined and determine the behavior of f near these points. Okay, so we're also going to determine, if we can, the behavior of f of x for very large x values. So basically, we're looking at asymptotic behavior. Okay, so let's go ahead and check that. Well, this thing is not defined. The domain of f is such that it's all x's, such that x is a real number. X can't be 0. And the reason x can't be 0 is this guy right here. So we have a situation where 0 is not in the domain. So let's see what happens around 0. So what we want to know is, what is the limit as x approaches 0 from the left of the function, and then we'll check out the limit as x approaches 0 from the right. So this is the limit as x approaches 0 from the left of x minus 1 over x. So what happens to this guy? Well, as x approaches 0, okay, this guy becomes really, really large. Now, as we're approaching 0 from the negative, so this will be 0, and then this will be minus. Now, this will be 1 over a super small number that's negative. So we're going to get this right here is going to end up being a plus, like this, and then this is going to increase, become very large. Okay? So it's large in the positive direction, so this will approach infinity, like that. Now let's go ahead and take a look at the limits as x approaches 0 from the right side. So that'll be the limit as x approaches 0 from the right of x minus 1 over x. This guy will go to 0. This guy will go to, this right here will go to infinity, but positive, so we have minus an extremely large number. So this will go towards negative infinity. So what we've got here, and that makes sense because of the symmetry involved. Okay, so what we've got so far, what we can tell, let's just draw that a little bit better. I don't think that got any better. Close enough. Okay, now, here's 1. At 1, excuse me, not 1, at 0. Here's 0. At 0, we know that there's a vertical asymptote here. We also know that as we come in from the left, we approach positive infinity. And of course, as we come in from the right, we have to approach negative infinity. And that makes sense because of the symmetry involved here. Okay? Now let's go ahead and take a look at what the next piece. Oh, they also want us to take a look at the ends out here. Okay. So as well on this, we want to take a look at what is the limit as x approaches positive infinity. Okay, so that's x minus 1 over x. Now, what we're going to do is I'm going to just divide everything here, okay, by x. But even if I divided everything by x, actually I'm not going to do that, because if I divide everything by x, it's still not equivalent. Okay, if I divide the whole thing by x. So here's what I'm going to point out. As x becomes really large, this guy goes to 0, this guy goes to infinity. And so this whole thing will approach positive infinity. So what's going to happen here on the ends is this, towards this direction, is going to head up this way. And then as we take a look at the limit as x approaches negative infinity of x minus 1 over x, well, this guy will go to 0, so it's not going to matter anymore. This guy will go towards negative infinity. So it'll drop down like this. Okay. So now let's go ahead and take a look at part 3 here. Part 3 asks us to locate minimums and maximums of f and determine the intervals on which the function is increasing and decreasing. So let's take a look at f prime of x. That's going to be 1 plus 1 over x squared. Okay, so we'll go ahead and we'll take the derivative of this guy up here. Of course, we get 1 for the first guy, negative 1 times the negative outside gives us positive, and we add 1. Well, we subtract 1 from this, but we add it when it's in the denominator. Okay, so now our critical values are when f prime of x is equal to 0, and this, guys, can never be equal to 0 because, let's think about this, this is 1, and this is always positive, so we're always adding a positive number, so this never occurs. So that means there are no mins or maxes. There's no min or max. Okay. Where is it increasing and decreasing? Well, it's increasing when f prime of x is greater than 0, and it's decreasing when f prime of x is less than 0. But this is the only guy that can occur because this is always positive for every x value, no matter what you plug in. So it is always increasing. So from left to right, we're increasing. So from negative infinity to 0. Now at 0, there's nothing happening because it's not even defined. And from 0 to infinity, we are, I guess I've already said it, that we're already increasing. Okay. Now we'll take a look to see if there are any inflection points. So that's f double prime of x. Now you got to ask yourself, if there weren't even any cases for mins and maxes, are there going to be any cases for inflection points? Okay, so let's just check here. The derivative of that is negative 2 over x to the third. And this is clearly never equal to 0. So since this is never equal to 0, okay, in that situation, then this guy says right here that we have no inflection points. However, we can use this to discuss concavity, okay? And so, for part 4, the issue is we'll take this function right here, f double prime of x, which is negative 2 over x to the third, and we'll ask ourselves, when is it positive and negative? When f double prime of x is positive, when it's greater than 0, that means the slope is increasing, which means that we've got a situation where we have concave up. If f double prime of x is negative, then we have a situation where the rate of change of the tangent line is decreasing, meaning the slopes are getting less and less positive, okay? or they're getting more and more negative, however you want to think about that. And so that is concave down. So f double prime of x, since it's this guy, for the x values that we're looking at, whenever x is negative, this guy is positive. So over in this range right here, we are concave up. Okay, so it is positive whenever x is negative, and it's negative whenever x is positive. So on this side over here, we are concave down, like that. Now they say plot a few pieces like x-intercepts and y-intercepts, so let's just go ahead and talk about those because it's good for us to do. X-intercepts are when the y value is 0. So we take our original function, which was equal to x minus 1 over x, and we ask it, when is this guy equal to 0? Okay, so when is x minus 1 over x equal to 0? Well, that is when x is equal to 1 over x. And these guys are only equal to one another when x equals 1 or negative 1. Okay. So when x is 1 or negative 1, we have an x-intercept. So here at positive 1, and then here at negative 1, we've got x-intercepts. Now what about y-intercepts? Well, y-intercepts occur when x is 0. But we know x can't be 0 because 0 is not an element of the domain. So there are no y-intercepts. Okay. That's pretty much all we need to know here at this point. Let me see if they've got anything else that they want us to do. Yeah, we're pretty good there. So we know that our graph must look something like this and something like this. Concave up, concave down.